supply.
2 loop, 2 power supply.
I solved for ID first and got a negative 2, so I knew it was going to go, like, I knew it was actually going to go the other way, right?
Okay.
But I still plugged in that negative to the second equation to solve for IA, and I ended up getting IA right, but ID and all the rest wrong. So I'm wondering how that works, because, like, I used my answers when I solved for IA.
So for 1, you should have put it in your negative value. Because we're assuming that we have. Yeah, because we're assuming that we made them clockwise to start with.
So that's where I did it wrong. I put it in the positive value.
Yep, and it's a little bit off, but we can go through that. We've just got just a couple of other things to talk about in math, so we'll do a 2 loop real quick.
So the answers for those quizzes are written as if they were still measured in clockwise.
Yes.
Everyone.
Yes.
So if you solve the whole thing counterclockwise, you're going to get every single one wrong.
Yep, because they'll all be negative. All right. We're going to do this real quick, and then we'll jump back into the math. Where does this one go? Positive on top.
So the only difference is you have a straight number with no variable on the other side of the second equation, really.
So say that again.
So the only difference between the one power supply and 2 power supplies, the second equation also has the constant.
Yep, would also have a constant in it.
Right.
All right, so come here. Source 1 is 33 volts, and it has a polarity of positive to minus from top to bottom. Source 2 is 21 volts, and it's also positive to negative top to bottom. R1 is 200K. R2 is 100K. R3 is 120. Yep, 120K. R4, oops, come on. R4 is 390K. And R5 is 220K. And the things we're looking for is IA, IB, and the current through and voltage through R2.
Should be the one going up and down.
Oh, did I flip those?
Yeah. I think so, unless I flip them.
Let me double check. Yep, I flipped it. All right, that is our equation, and we're going to solve using mesh. First thing we do is we're going to assume our directions, and we're going to assume them going in clockwise. And we're going to write our equations. So our Kirchhoff voltage loop for A, start here, go up and around. So we have a minus 33 plus R1 times IA, and that's the only current through R1, plus R2 IA minus R2 IB, because we have this current coming in, we have current B opposing it, and then R5 is R5 times IA. And then we set this guy equal to 0. Then we'll plug in our values. So we get 200K IA plus 100K IA minus 100K IB. And then we have plus 220K IA is equal to 33. So I'm just shifting that 33 over while I'm writing everything else down. Then we want to combine everything together. So we've got 200K IA, we've got a 100K IA, and we've got a 220. $520K IA minus 100K IB is equal to 33. So this is our first equation. Next equation, a Kirchhoff voltage loop for B. We'll start here, go this direction. So first thing we're going to run into is R2 times IB minus R2 times IA. Then when we come up, we're going to come around, so we're going to run into R3. So plus R3 IA plus 21. And then finally plus R4 IB equals 0. Then we're going to add our values back into it. So we have 100K IB minus 100K IA plus 120K IB plus R4, which is 390K IB, and that's going to be equal to a negative 21. We want to combine everything together. So we have minus 100K IA. We've got 220 and 390. So that gives us plus 610K IB is equal to negative 21. That gives us our second formula. Any issues there? Okay, I'll give you guys a second to get caught up for those who want to.
Hallelujah to that.
You never know when the teacher's going to do a pop quiz.
I like that.
I know. This is kind of like a threat.
Okay, so now we want to combine these guys together. So I'm going to bring our second formula over. And we can go a couple different directions. We can either get rid of our IAs or our IBs. Honestly, it doesn't matter which one we go through at this point. Get rid of A? Okay. So now as we look at our two equations, we have to get these guys to equal each other. Now what we can do, huh? Brute forced it? Okay. You can brute force it if you want.
When I said brute force, this is what I meant.
Okay. A lot of times you want to avoid decimals just as much as possible. Decimals start to convolute everything. So try and keep them in whole number increments. It just makes life easier. So now we're going to take these formulas. We're going to create our new ones. So we end up with 5.2 meg IA minus 1 meg IB is equal to 330. Anybody have any issues with those conversions? Okay. This one becomes a positive 2.1 meg IA. Oh yeah, we are. I was looking at these two numbers is what I was doing. Negative 5.2 meg IA. And then we have our 610. 31.72 meg IB. And then we have a 21 and a 52. $1092. Now we take these two equations, we combine them together, those will cancel, and so we end up with 30.72 meg IB is equal to a negative 762. You get there? Divide both sides by the 30.72 meg. And IB comes out to be times 10 to the 6. Come on. Negative 24.805 microamps. Everybody good there? Okay, now we're going to take this value that we got for IB, we're going to plug it back into one of our original equations, and again, it does not matter which one. So, We have the 520K IA minus the 100K times a negative 24.805 micro is equal to 33. Now, come on. So we have 520K IA plus 2.481 equal to 33. We subtract this over. So we have 520K IA is equal to 30.520. Huh? You have a negative times a negative. Divide both sides by 520K. And IA is 58.691 microamps. My guess is somewhere in there that a negative sign got dropped. Is my guess.
No, somehow messed up on the IB, but solving for IA, I was within 5%, so.
Yep.
So I wasn't far off IB, but I messed up the addition, something like that.
Right. Okay, so now, again, the answers to these quizzes are assuming that we have these two currents going clockwise. So, when we put in our answers, these are exactly what we're going to put in. What we got for IB, what we got for IA. IB will be negative. Now, we're going to take these currents, and we're going to go back in and solve for the other two components that we need. We need to solve for the current through resistor 2 and the voltage of resistor 2. So IA is 58.691 microamps. IB is 24.805 microamps. So when we come back up, we know IB is going counterclockwise. So when we have that, what current do we have going through R2? Both of them are added together. If it helps, draw the direction the currents are going in the individual resistors. That way you can see if you're adding or subtracting from each other. So in this case, IR2 is going to be equal to IA plus IB. So we get the 58.691 micro plus the 24, sorry. .805 micro. IR2 be right around. Huh?
You add it as a negative, like for.
Nope, because now we've changed it. To solve for the total voltage or total current going through that resistor, now we have to change it. But in the answers, we leave it as a negative voltage or negative current because we've assumed positive or we're assumed clockwise on all of our loops. So we get 83 0.496 microamps. We then take that, multiply it into our resistance, and what kind of a voltage do we get? How much? 8.35 volts. Usually in mesh, when we're trying to solve for things, we're usually just trying to solve for one voltage of a component. The idea of mesh and Kirchhoff's voltage loops, those are the key troubleshooting aspects that you guys need to try to internalize. What are all my voltages doing as I go around in a loop? Because there's going to be times you're going to be in a system where you're going to start off with some voltage. And each one of these components, like we did with the bipolar voltage divider, each one's going to require a certain number of volts. The current will all get taken care of itself. We build circuits to adjust all those. But as we're going through, we're like, okay, we have 100 volts to start with. We're dropping 10 from here, 10 from here, we're dropping 15 from here, we're dropping 25 from here. And so across this guy, we should have this much. Well, when you go in to measure them, you can quickly see how much does each of these systems have. Well, all of a sudden, one of these systems is taking 30 volts instead of 15 volts. So that's when you go in and you either try to calibrate it or you have to replace the module. And then you send that module out for repair, usually. So you guys will either be the ones pulling these modules off and shipping them off to be repaired, or you guys are going to be in the companies that are repairing these modules coming in. So it all just depends on where you guys end up getting a job. So there's multiple opportunities, and then everything in between. I'm not saying those are the only types of jobs out there, but those are just the easiest. Hopefully not. Those are people in lower campus. Now, I'm not saying there's not good jobs in lower campus, but that's why we're in the College of Tech. Let's be honest, that's why we're in the College of Tech, is to get better jobs. All right. Any questions about two-loop, two-supply? We solve them the exact same way as if they had one supply. We solve them the exact same way if they had 14 supplies. We could put that many supplies in there if we really wanted to. And we could make these circuits just as complex as we want. One of those original series parallel circuits I gave you, we could just solve with mesh. Where you got the 3 or 4 resistor branches out across, and it just starts to spread and explode. And we could add other connections in there, and wouldn't matter at this point. You could solve it using mesh. You could have a delta to Y, a bridge circuit inside of a bridge circuit inside of a voltage divider, and be able to solve using mesh if you so choose. This is life, though. Electronics is life.
Bro, I just know this is school, man.
Yep. All right. Does that answer your question, Max?
Yeah.
Okay. Kind of the long way around to get your answer, but. All right. So continuing on from where we were yesterday, we were talking about imaginary numbers, complex numbers. We're starting to get into those. Again, the whole idea between the imaginary numbers is to understand that in certain circumstances, as you get more and more electronics, you're going to have instances where you have to solve for large powers of I, okay? And they just are going to follow the same pattern every single time with the 1, I, -1, and -I. It's going to cycle through those depending on the power. It's not a common thing to have to deal with powers of I to the, to the 502nd power, but you can calculate whatever comes up that you might get. Huh? Yeah. But at least this way you can correct Google when it is wrong, which it is from time to time. Okay, so continuing on with that, what we're going to talk about is specifically the idea of I. What is I? Okay, what did we define it as yesterday? The square root of -1. So we can now take this part of the equation out and give it the variable I, or the constant I, things like that. And so that way, when we come in to solve for problems, if we have this problem and punch it into our calculator is going to puke. Does not like it. Yep. Calculators are only so smart. The idea behind this is we can separate this guy out, so we have the square root of -1 times the square root of 52. It's just a power that we're splitting apart. So when we get to this point, what does this become? I. So now we can just put that into our equation, we put it in there, and then when we're solving for it, we throw it back into the equations and things are going to work out. Because a lot of times we're going to have another I in there that we get squared at some point, and it's going to turn into a -1. Because when we square a square root, we get just the value underneath the radical. This guy, we're going to split up. What are the factors of 52? Huh? 26 and 2, and 13 and 2. Now, remembering way back when, probably deep in your memory banks, from when you learned these in high school, when we have squares underneath the radical, we cancel and bring one of them out. So what this would reduce down to a lot of times in this instance, what you're going to do is I would combine these together. So we have the 2I times the square root of 13. Otherwise, that I could be lost and get back up underneath the radical. Only one. So the two 2's get canceled out because underneath the radical. Because what you have at this point is 2 squared raised to the 1/2 power. It does.
Not just like you separate the radicals, so it'd be like radical 13 times radical 4, and then the radical 4 is multiplied by 2.
Right, yeah. Like I said, there's different ways to go about that. That's just kind of combining them all together. Whatever you guys are most comfortable with, use those. But the idea is, when we reduce these down, we can get to these values. One thing you cannot do, because this will break the convention and it'll basically throw you into an infinite loop, you cannot take the square root of 52 and convert it into the square root of -1 and the square root of -52. Because as you start doing it, you're always going to be swapping in and out i's and everything, and you're going to end up with a mess. You end up into an infinite loop.
Yeah, I don't understand the reasoning behind that. It doesn't make it more complicated.
Some people have tried to do it. That's why. You can't do it. So this, don't even think about it. But if there's already a negative underneath the radical, then yes, you can do that. But you're right. This is introducing something else underneath that radical, and we just don't need it. It's not necessary. So that's the idea here, is now we can solve for these values. Now this is starting to become a complex number. We have our variable, we have our indicator, which is I, which is, like I said, when we start getting into these next week, we're going to start talking about polar to rectangular notations and things like that, we're going to get into this idea of where we have an imaginary number, where this imaginary number is coming from, because it's related to the reactance, which is the opposition to AC in capacitors and inductors. And then once we start in AC, all this stuff is going to come flying together on the first day. So, with complex numbers, when we have a numbering system with our graph, we're going to be changing things up a little bit. Normally, when we look at a graph, we have our x values, we have our negative y value, negative x, and our positive y. What we've done is we're changing places for the y-axis on our graph. We're changing it to be our i's, our imaginary values. And the way this is going to look is we have our positive imaginary, we have our negative imaginary. They're going to function and work the exact same way. But the idea here is anything on this imaginary scale isn't real, hence imaginary. We can't physically measure this value. And like I said, the way to think about it is the reactance of AC components, because they're dependent on frequencies to operate. So what happens is this is our imaginary axis up here. On our x-axis, this is our real values. So this is like resistance. These are voltages. This is pi. Things like that we can touch. And on this scale is our imaginary, which is going to be our reactance in a couple of weeks. Each component that we mess with, and even the ones we're doing now, in lab right now, we're measuring across resistances. They still have an imaginary value, if you will. It just happens to be 0. So we ignore it. Inside of a resistor, there's nothing that's going to react differently between 1 megahertz, 6 megahertz, 2 millihertz. It's not going to change. So there's no reactive components in this component whatsoever. But like I said, capacitors and inductors are. Yes?
It's like what we see on the one things that are in there with the screen.
The scopes?
Yeah.
Yep. You can track these on those.
They're like always right in the middle of the flat, except for right when you turn rotate.
Yep, you have a little bit of a surge and then it levels off and goes good because it's changing. You have some sort of a frequency in there. Like I said, this part has always been here with every numbers that we've always done. We have just ignored it because it has 0 reactive or imaginary components to it. It's always been there. We just don't care. So what we're doing is we can chart these guys out in a couple of different ways. We can give our coordinate just like we would doing with the graphing part. So if we have a coordinate over here, let's say this is 3 and 4. Okay, now I know my drawing's off a little bit, but we have our coordinates 3 and 4. We could write that as a point in space as 3, 4. We could also write that as this. So 3, 4 is equal to 3 plus j of 4. So now when we have these components where we're mixing both real and imaginary parts together, we can separate what is what. What's the real part? What's the imaginary part? The other thing we could do is if we had, say, multiples of these guys. So let's say this was the equivalent of some resistance value. Okay? It's in electronics, we're going to call it impedance because it's a combination of both resistance and reactance. Okay? If we wanted to add these guys together, let's say we had another resistance that was 4 and minus j of 3. So that would say if we plotted these on the same chart, we would have another point down here in space. So then when we combine this together, again, we're going to add our similar terms. So we end up with, so we add our real terms together and we get 7. We add these two together, basically plus j of 1. Okay? So if we wanted to combine these together, so 4, that's what we would get. Just like if we were to combine these two angles together. So one way to look at it is if we have lines, it's the combination of those 2 points. And I know my lines aren't straight, but that's the idea, is we can combine these guys together. This is known as rectangular form because we are using the x and y coordinates to form a rectangle. Do what? Well, that's one thing that we're going to be talking about. We won't get into it until a couple weeks, but yeah, we can represent a sine wave as an angle on this graph as well. When we get into AC, we'll talk about all that. These are just the very, very, very basics. Okay? That's the whole, that's the idea, is imaginary, it exists, but we can't physically do anything about it to measure it. It's there, we can see its effect. So this kind of comes into the whole cause versus effect thing. Sometimes you can observe the cause and know what the effect is going to be. Sometimes you observe the effect and you have to summarize what the cause was. You can't see both sometimes. And that's where we get, and that, unfortunately in electronics, that happens quite a bit. Is you're going to see one, but not necessarily the other at the same point. But we can calculate it and know how to mitigate it. So the other way we can look at these guys, so this is rectangular form. What we also have is with these points in space, we can look at them as vectors. We have a particle that's going some distance at some angle away from our reference line. So this same spot here, we can identify this as a value at some angle. And basically what we're saying is it's traveling so much distance away from our origin at an angle based of our reference. This is polar notation. And both of them are completely correct.
So polar notation and rectangular form are like similar?
Yeah.
Okay, so they're like, what's the word? Like substitute?
Mm-hmm.
Okay.
And there's times where we will. One of the things that we're going to do next week is we're going to learn how to go back and forth between these. Yep. We're going to touch into trig next week. Yep, with radians, angles, degrees. We're going to get into trig. But the idea here is we're actually applying the trig. We're not just making angles, we're not just making triangles, it all has its purpose. And the purpose is these relationships between these notations. Because the difference is you can add and subtract and you can multiply in rectangular form. You can do that. You could multiply these two values together if you wanted. What would happen when you do? What are you going to get? You're going to have I squareds and i's, which goes back to what we learned this week about understanding what an I squared is.
Why would you, like, is there a reason behind multiplying that?
You're going to find currents, voltages. AC has angles. So in rectangular form, we can add, subtract, and multiply. In polar form, we cannot add or subtract unless they're the exact same angle, and that happens few and far between. Pretty much. So in polar notation, we multiply and divide. So there's going to be times where we have to go back and forth with our number depending on what we need to do next. We're going to talk about those conversions next week. This is just kind of an introduction to what is this that we're looking at. So, where is my mouse? You can't, you're stuck. You signed your soul away.
Yeah, do they have to go to class every single day?
Lower campus?
Yeah.
No.
See, that sounds kind of nice.
Just want to take it back,
A few
man.
years of school for you to go through.
Well,
I know, especially a 3-year degree is pretty good.
I was kind of done with school when I take the.
So, for example, in the quiz, we're given this question. The square root of negative 36, and we want to convert it to its equivalent. You get this one? Okay. So, in the options that we have, we're looking at plus or minus j times some value. So you have the option to select plus or minus and then type in your answer. Where's my mouse? Okay. Yeah. Yep. So we're going to have plus or minus j times what? Times 6. So we get the square root of negative 1 times the square root of 36. This becomes positive j times 6. I usually do just so it doesn't get reabsorbed into the system. Yeah, because if you put the j here, sometimes when I write this kind of trails off a little bit. So I try to put that in front so I know it doesn't go in. The other thing I do is I put a hook on the end of my radical sign. So anything after that hook does not go into the radical. Okay, here's another question that we have. We have the square root of negative 49 times the square root of negative 36. So you got 7j times 6j See, would our calculator even do that? I doubt it. Yep, it won't even do that, even though it works out to be a good answer. Calculators. Well, it doesn't believe it. Doesn't believe in imaginary numbers. Okay, another example with complex numbers and with imaginary numbers. If we have, where was the question I wanted? Three plus j squared 10 minus j squared 2 plus j squared 9 plus j. What's the final answer? What do j squareds become? Negative ones. So 3 minus 10 is negative 7. Plus 2 is negative 5. That's what we're looking for in the homeworks for these. Just the very, very basics. Yes. Plus. Because it's not multiplied, yes. So that's the type of questions we're going to be looking at for complex numbers. For imaginary numbers, come on, load. The idea is you're going to have some of the powers of j that you'll have to go through and solve for. So j to the 6th is equal to what? Negative 1. And why is that? Why do you guys say negative 1?
Because even though it's a 1, and then the 6 is negative.
Okay. Can I split that up? J to the 6th is j to the 3 times j to the 3. Comes out negative 1. So all we're doing is when we're given these values, we just want to separate up into the known values that we have. So all you guys need to memorize is the four base powers of j. 0, 1, 2, and 3. And then also know that that pattern is going to continue when it gets into the negative. Let's see. And that's what we're looking at for imaginary numbers. Like I said, there will be positives and negative powers on those. The pattern just continues on up through the negative values as well. All right. So same with complex numbers, we're going to have different scenarios like this, where you're going to be having different values to add and subtract together. You're going to be adding and subtracting radicals, and also multiplying these guys together like I was talking about. There's going to be times where we multiply them together. So we have 2 plus J4 is going to be one resistance value. So if let's say you had a resistor and a capacitor in parallel, you have to find the total impedance. You can use the product over the sum for these guys. So let's say this was our resistor value. Let's say this is our capacitor value. We want to find the total impedance of this guy. So let's use product over the sum. Is what we would do. This is only going to get us so far because, like I said, I haven't taught you guys the conversions on how to convert these back and forth to polar and rectangular. But what we would end up with is we would have 6 minus J4 plus J12 minus J squared 8. And then this would be over 5 plus J2. So all we did is we're just multiplying those guys across. We're foiling. And then this one we know J squared is what? -1. So this becomes a positive 8. These guys are going to add together. So we end up with a plus J8. And we have a positive 6 and an 8. Those will combine together. So the top part is going to end up with a 14 plus J8 divided by 5 plus J2. So now this is as far as we would go on the assignments today. You're not going to have anything this complicated, but I just want you guys to see this is where we're going with this style of math. So what we're doing is we have 2 resistance values. We're going to solve and find the total impedance of this guy. We multiply on the top, we add on the bottom, and then in this time we're going to have to convert these guys because we have to divide. But as of right now, this would be our correct answer, because that's as far as we can go at this point. This is on the very most extreme complex style that you guys would see for the homework. There may be one in the entire question bank, and it won't even be this difficult. It would be a combination of either adding values or multiplying values, and then simplifying them down into so you have a single J value versus J to the powers.
So this is as hard as it gets for now.
Yes. This is as hard as it gets. This, like I said, this you won't see this style on the quiz, but this is where we're going with it. Ouch.
But normally, aren't you not supposed to have an imaginary on the bottom?
You can. I mean, we will, because we will get to the point where we'll divide this out and we'll turn it into one solid value.
Yeah.
But for this, yes, we ended up with it on the bottom, but normally we would finish it out, so we didn't. Okay. With that, let's go to break.